the second order, so that, I mean, for once you can see how these things get going. So we'll finish it off today. There's no doubt about that. But coming back to where we were, it's the free energy which we got, Ginzburg-Landau model, which we started out with. So if I just write it in Fourier space to begin with, it is m squared plus p squared by 2, phi p, phi minus p, plus lambda over 4, phi p1, phi p2, phi p3, phi p4. Phi minus p1 minus p2 minus p3. Good. So we were in the business of calculating the partition function, which is integral d phi e to the power minus f. And the idea was that what one is supposed to do is integrate out. So the philosophy is that integrate out large momenta and write the f as a part which belongs to go to a f which belongs to f phi small, integrating out this large momenta, meaning that phi p is written as phi greater or phi lesser p plus phi greater p. The final cutoff, looking at the range between lambda b and lambda is the real cutoff. I'm focusing on a scale which is lambda over b and talking about this range which is below it, that is the lesser, and here is the greater, which I will integrate out. Integrating out, I will get f phi less, and I will make it look like this by scaling the momenta back by a factor of b and doing a rescaling of the field. So I'm back to this, and I get a f phi prime, which looks like ddp once again over 2 pi d, but now it is m prime squared plus p squared over 2 phi p phi minus p, because I have restored, and then it is lambda prime over 4 phi p1, phi p2, phi p3, phi minus p1 minus p2 minus p3. That is where we were headed, and it is a question of finding m prime squared in terms of m squared and lambda prime similarly in terms of m squared and lambda. That is the goal. And we are, I integrate out these, and I'm going, so that is obtained by, that is done by looking at the partition function. And in the partition function, this is the full partition function, and you keep d phi less, and you break up your f as f is equal to everywhere I have to write m squared plus p squared over 2, and it is phi greater, phi p less times phi p minus p greater plus phi minus p less, and then similarly with the plus lambda over 4, and you have 4 such terms sitting over here. So that's what you would be, and you expand it out, and you see that there is the lesser. There would always be 5p less, 5p less, and all of these with 5p less. So I'm sure to pick up integral. This is dd p of 2 pi to the power d, and then it is m prime squared plus p squared over 2, 5p less, 5p less, and then plus lambda prime over 4, and then it is 5p1 less to 5 minus p1 minus p2 minus p3 less. So that part would always be there. And then there is the part where things are getting mixed, and this is d5 greater, and the mixing, when it is an odd number of 5p greater, since I will be doing perturbation theory, the perturbatively, when I integrate it, odd number of 5p would not be contributing. So all that I'm interested in looking at is minus m squared plus p greater squared over 2, 5p greater, 5 minus p greater, and then the part which is minus lambda over 4, and I have 5p greater, 5p greater, 5p less, 5p less, and then I have minus lambda over 4, and there would be, so you are expanding to the power 4, and then there is 6, which has the 2 and 2 has a factor of 6. Those with a factor of 4 would be 3 and 1. So I don't need to worry about those. And there is another which is all greater. There are then 2 which I have not written down, which are like 3 greater and 1 less, or 3 less and 1 greater. And yeah, and I have ignored them because it's going to be done perturbationally, and when it is when I expand this as well and do the, it's an odd number of 5p greater, and therefore I don't have to worry. All right, and then the way to do it, you first expand this as 1 minus, this is 3 by 2 lambda, and it is 5p greater, 5p greater, 5p less, 5p less, and there are all those which are greater, which again I have to expand. And that is, this is first order, then comes the next order, and so on. And outside over here sits this e to the power minus m squared plus p greater squared by 2 phi p greater, phi p greater, integral with over d phi. And then what you do is you multiply this by through and evaluate the integrals. Actually evaluate the integrals so that the answer is finally d phi greater e to the power minus m square plus p greater square phi p greater phi p minus p greater and 1 minus 3 by 2 lambda, the expectation value of phi p greater, phi p greater, phi p less, phi p less. So there would be the expectation value of this, but 4 phi p is just that's just going to get me a number. So I'm not interested in actually writing this down. So yeah, you are yeah. So and then I have to go to the next order when it is going to be. So this exponential over here, which you are looking at, has to be expanded to, I mean, all the necessary orders. And so it is going to be, I mean, this that I will be picking up the order lambda square over here, which would be having phi p greater, phi p greater, phi p greater, phi. These are not, I mean, right, sorry, should have been, sorry, minus p to minus p3. And then so there is going to be this, these are with the, and this is with the minus p1 minus p2 minus p3. And this would be clubbed, I mean, with another set, which is, so you are expanding this quantity over here. So there is this one set which is summed over this dd p1 and so on, and then the other which would be multiplied by ddq and this it is phi q1 greater, q2 greater, q3 greater, and the other one, and terms like that. So at order lambda square. And so it is a question of actually what I'm doing is I'm integrating out this quantity over here. I'm expanding out this quantity over here, or the greater part, and it is what I'm expanding. Let me not expand the greater without anyway. I mean, there is going to be, or let's say, I have this 3 by 2. There are quantities over. Is the 6 right? Is the question. It is. I'm looking at. Sorry, maybe the 6 may not minus p less, and then I have. Do I have the 6 is what I just want to check. It is phi p greater plus phi p, then it is the p1, and then it is greater p2 plus phi p2 greater less phi p3 greater plus phi p3 less into this. So there would be terms where there are I mean 2 greater, 2 less. So there are these, I want to pick up 2 greater, 2 less. So it is this with this and this with this. So that's there going to be there. and then I would be having, so it is, how many of them is what I'm after. I can go and connect this to any one of the other three. So that's three ways of doing that, right? So it is three ways of doing that. And then I have, so I can connect this to any one of these three, which the remainder three. So I connect, I get two, and then I still have, once I have got phi, and then I don't have a choice, right? If I do this with this, then it is automatically this with the other. And so if I write phi P1 greater, phi P3 greater, then it has to be, I take P1 and pick up P3, pick up P2 or pick up P4, and then it is automatically the others would have to follow. So it is not 6 of them, but rather 3 of them, right? Isn't that right? This is important, so I better get this right. It looked like 6 now. I'm saying it's 3. So I have 4 of them. It is phi P4. No, phi P4 greater plus phi P4 less, and I can go and connect with any 3 of them. So I can take this and say that I form a combination with any 4. So that gives me 3. I can go with this, I can go with that, I can go with this. And then the other 2 don't have a choice, right? The other
the structure we are after is phi greater, phi small, phi small.
Yeah.
Okay. So there are 3 P1. I can, for phi greater first term, I can say that it can be P1, it can be P2, it can be P3, it can be P4. So 4 possibilities. And then I have remaining 3 possibilities for the next term.
Yeah. Yes, right. I was going by the, if I expanded it out, then the binomial expansion would be, this is to the power 4, 1, 4, 6, 4, 1. Right? So 1, 4, 6, that is what made me write 6. So, but is the 6, or do I have 6 of them? Or am I making a mistake? There is the momentum to if I look at it as a plus b, and if I take to the power 4 and I may expand it out, it is like a plus a to the power 4 plus 4 a cube b plus 6 a squared b squared. No? So that is what was driving me for the 6. And now if I look at it differently, there is, if I pick up this and connects with that, the point is that this could have connected actually it could have, this leaves out the, it is the less, I mean, I can do this and this, and then it is the, but then there are the minuses. No, I simply looked at this, but then there are the minuses which are going to play their own game. That is going to double the tree, right? I simply looked at terms which look like phi greater, and there is the, no, there is no minus. It is greater, 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 greater. 6, not but it is greater, greater, less, less. Right? So greater, greater, less, less. And I'm looking at, if I multiply it out, there are terms which all, 4 terms which are all this, and then it is all great has to be, or 1, all less is 1. There are, I mean, 3 greats and 1 less is going to be, you take this, this, and this. I mean, it is 4C3, right? I mean, there are 4 greats, and I pick 3 greats out of them, that is 4C3, which is 4. And once I have 4C3 fixed, how many, once I have picked up 3 of them, so this, this, and this, let's say, then I have no choice but to go with this, right? So, that is, if it is greater, 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 the only less is this. So then, therefore, that is 4C3, and that is, the answer is 4. But now it is greater and greater, so I want to go greater and greater, lesser with less and less. So I go and connect with this 5P1, 5P2. That is the greater. Multiplying that 5P2, 5P less can, so with the, it can only combine with, right? If I have 5P1 greater, 5P2 greater, then I can only have 5P3 less and 5P4 less, right? So similarly, if I have this and this, then I have, but I get, so 5P1 picks up 3 possibilities for me. Then I'm leaving out those with 5P2. So the leaving out, so then I leave out this, and I go 5P2, and I pick up the possibility that it is 5P2, P4, 5P2 greater, 5P4 greater, 5P3 greater, right? So
6 in the long. The first case P1 and P3. তারপরেরটার জন্য আমরা দুটো P2 এর দরকার।
This can go with this, this and this, or it can go this, 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 and this, right? Or it can go this, this, and this. No, that is taken care of. It can only go, this can go this, this, correct? I mean, this can, the 3 which I have 3 greater, which I have not taken into account, I've gone with phi p1 and I have picked up graters with these two. But I have obviously left out a greater which is phi p2, phi p4 greater, and phi p3 greater. No? And then have I
So, what is the matter point? Five greater, five greater, five P1 greater, five P2 greater, five P2 greater, five P1 greater. But it's different objects.
no, they are not different objects. No, phi p1 greater, phi p2 greater, and it is all that I do is all that I want to do is write out, multiply this out, and how many terms with 3 greater, 1 lesser, right? So 3 greater, 1 lesser, that is the or 2 greater, 2 lesser. So 2 greater, 2 lesser, that is the one. Acha, the 3 greater, 1 lesser is 4, right? That is the point. That 4 is clear. That this goes with all 3, and then this can go with only 1. So that is 3 plus 1, which is 4. Now you look for 2. So 2, this can go with this, and this is there are 4 graters over here, and therefore it has to be a 4C2, right? I mean, I can combine phi p1, phi p2, I can do phi p1, phi p4, I can do phi p1, phi p3, but I can do 2, 4, 2, 3, and I can do 3, 4. So there are 6. So the 6 was right. হ্যাঁ 4C2 করেছিলাম, but then I thought যে overcount করছি কিনা. So sorry, I had it right. So anyway, very good. So nothing there, nothing to worry about. So that is correct. And then it is order lambda square. So this is minus 3/2 lambda. And now I'm looking at the order lambda square terms. And it is lambda. So now I need the combinatorics over here, that there is phi p1, phi p2, phi p3, phi minus p4, and then there is a phi q1. Then I'm looking at phi q1, phi q2, phi q3, and phi minus q1, minus q2, minus q3. So that is the next that I'm looking at, and you have to go. It is the non-trivial is when this group connects to this group over here. So that is the non-trivial connection, and I can connect. So the thing is that it can, we are looking at greater, greater, lesser, lesser, greater, greater, lesser, lesser. That's I can have that, or I can have 3 great, 1 less, or over here also 3 great, 1 less, 1 great, 3 less. So there are these various combinations that I can have, which is phi p1, 3 greats over here. So 3 which are great over here, 1 less, and then there can be phi 1 great over here and 3 less. Or it can be the other way around, that phi less and phi 3 of phi less over here, and 3 and 1 over here as well. So there can be there can be 3 less, 1 great over here. More importantly, there can be 3 greater, 1 less over here, and 3 greater. So let's go 3 greater, 1 less over here, and 3 greater, 1 less over here. And so it is 3 greater, 1 less, 1 greater, 3 less. There can be 3 less, 1 greater, the reverse of this. So there is 2 great, 2 less, 2 great, 2 less, 3 great, 1 less, 1 great, yeah, and 3 great, 1 less over here. The greater, so these are the two which one has to look at, because this says that there are these 4 lines coming out over here. So there are 2 less coming in, and there are 2 greats growing over here. And this is a less, and this is a less, and this is a great, and this is a great. And these connect. So these connect, and therefore this is of the same or kind as essentially correcting the fact that there was a vertex over here. That vertex has now become a loop over here. So essentially this is a correction to this. Whereas if I look at, so that is this picture, that 2 less, 2 greater connecting with 2 less, 2 greater. If you want the other one, which is 3 greater, so you have 3 greater and 1 less. So 3 greater and 1 less. This should have been less. So I have these 3 greaters and 1 less coming here. So there is this 1 less which is like this. There are 3 greaters which look like this. So there is a less over here, there is a less over here, and then you have. So this is less, less, and this is greater, greater. So here is a correction, but now what does this correct? This corrects the propagator over here. At the single loop, I had drawn a correction which is like this. That is the one which we had looked at in details. That is the term which is just this one over here. And that has this structure. So, and now you are saying that when I go to order lambda square, I would be picking up this over here, this correction which you see over here. So that is the correct, that is a correction on this part over here. There is going to be another correction on that part over there, which is going to look like this over here, which says that, look, I have less and less, and then there are 3 greater and 3 greater over here, and they can connect as, I mean, you connect these 2 greaters among themselves, these 2 of these 2 greaters among themselves, and the 1 great and 1 great coming and forming this. That is, I have a 5 greater connection over here, I have a 5 greater connection over here. The outside ones are 5 less, 5 less. This is 5 less, 5 less. Here is 5 less, 5 less, and so on. So the 5 less, 5 less, which is what we are interested in, gets dressed by just this one at the first order, lowest order in lambda. At the next order gets dressed by this and gets dressed by this. This one is just the square of this one and simply says that everything becomes all the diagrams which come the first time have to come as a GP series. So these simply go in the GP. So once I have done this, I would ignore these because this I know is has to happen. This term has to be there because things have to look like a GP series in each distinct diagram. But this one is new. So this is going to be a non-trivial correction over here. So that is of all these second order terms that I'm going to generate. These are the terms which correct the phi less word. So they are going to show up as corrections to this term over here. This term, as we had seen, is a correction to this is a correction to this m square over here. These are corrections to the m square at order lambda square. This term on this graph, on the other hand, is a correction to the vertex over here. So what you are looking at is essentially you are looking at two sets of diagrams. One of them corrects the m square over here and the other corrects the coupling constant over here. You would be generating as you go along in this scheme, you would be generating other kinds of coupling constants as well, because the next order would bring you lots of lesses, and the greatest would be integrated over. But those would be bringing but you know, when you started out, that if somebody gives me 6 terms, a 6-term answer, that is not going to be relevant. The only coupling constants which grow for d less than 4 are the m square over here and the lambda over here. So if I generate 6 phi lesses, I don't care, because they are going to go away as I go towards the as I go to go through the renormalization process again and again. So only those which have a dimension, this one had a dimension 2, this had a dimension 4 minus d, and the phi cubed had a dimension of 6 minus d, and so on. So the point is that if d is equal to 3, then it is only the d minus, if you are d equal to 3, then it is the d minus 4 which is important, and the other side. Rather, the other one is a 2d minus 6, which is d minus 3, and then it is the 3d minus 8, and so on. So this goes as 4 minus d, this goes as 2, the next one goes as 6 minus 2d, then it's 8 minus 3d, and that's the series. So if I'm willing to work between 3 and 4, 3 is marginal, then I can settle with 2 and 4 minus d. So all the others which I generate are useless, but these are useful. So this is the this being the story. I have to. So what do I do? What do I do is I look at, I'll pick up I first, let me get rid of the part which is saying that this is going to be dressed by this line over here. So I look at just the first first term over here, which is minus 3 by 2 lambda 5p greater and this. So this is saying what you are going to do is that your point is I evaluate this thing and put it back in the top. So I evaluate this and put it back on the top means that it is 1 minus 3 by 2 lambda, and then it is this integral, it is phi p less, phi minus p less, and I'm integrating out over the graters, and then it has to be 1 ddp over 2 pi to the power d 1 over p square plus m square, and going from 0 to lambda. So that's the over here, not from, sorry, it is from lambda over b to lambda. So it is lambda over b to lambda, and this. So then you re-exponentiate it, you re-exponentiate it so that it looks like z is integral d phi less, and you are looking at minus m square plus p square by 2 phi p phi minus p, and then it is minus 3 lambda by 2, and it is phi p phi minus p, and here I have an integral lambda over b to lambda and ddp over m squared plus p squared. So therefore, what has happened is that what this is saying is that at this stage, m square has gone to m prime square, which is equal to m square plus 3 lambda over 2, and then it is integral lambda over b to lambda ddp over m square plus p square. So this is where one stands with this order. Where am I with the next one? With the next one, it is going to be, so all right, I now have to look at the so I'm only interested in 2 less. I'm going to the second order. So this is, as I said, all this is going to be 1 minus 3 by 2. This is now this order. And then you expand the next order. So it is 1 minus 3 by 2 expectation value there, and then it is we started expanding the all right. Let me not put the 6 over 4 over there to be to start out with. It is lambda over 4. All right, might as well. Eventually would. It is just trying to get the shortest way of getting the. I do want the lambda square, the relevant term, right? It is. I have expanded this over here. I have got 6 terms which are lesser and lesser, so I better keep that 6 over there. 1 term which is all greater, and I have 1 which is all less. And all right, I am not going to, I should be writing down, yeah. So all right, I should be, in principle, I should all be writing down the 3 greaters and 1 lesser, and 3 lessers and 1 greater. But as I said, the correction to this lambda, the correction to lambda will have to come from that graph which looks exactly like this. So when you come, the correction to this would have to be this over here, because this part is simply pictorially looks like this. And when you have a second order, then you have two of these, and only connection, this is greater, and here is less, 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 and less. And when you integrate out over the graters, you are left with 4 terms which are less. So that is why it is only the, when you look at this sequence of terms which are a mixture of greater and lower, in order to generate this, the only term I need is 2 greater, 2 lesser. I don't need the 3 greater, 1 less, or 3 less and 1. Huh? So that is why I can safely get this one down and write it is plus 1, and then this is one where I will go to second order and write it is 1/2 and times lambda over 4 squared, and there is 36, and coming from 2 of them, and I have phi P1 greater, phi P2 greater, phi P3 less, phi P1 minus this minus P1 minus P2 minus P3 less, and phi Q1 greater, phi Q2 greater, phi Q3 less, and phi minus Q1 minus Q2 minus Q3 less. So less, greater, less. Right. So this is the term which is going to correct the coupling constant. The coupling, so when I'm finished, then I will be having, this is 2 grades, and the 2 grades over here would have to combine, and that would give me, so the combinatorics, then these are untouched, the lessers don't come into picture. It is, this has to combine with that. P1 can go with P2, and P2 can and this, or the other way around. And so there are 2 ways of doing this, and therefore the 2 goes out, and I have 36 into lambda squared by 4 into 4. And I have this loop over here, which is 1 over, I mean, this is what do I have? It is phi P1, phi minus P1, and then it is times. So it's P1, let's say, has gone with this, then it is P1 and P2. So this is P1, this is P2, phi minus P2, these 2 lines over here, and that's the still 1 more minute to get this through. So this is it. Now I want to, I mean, what exactly is this? I have connected phi P1 with phi phi P1 with phi minus Q, this with this. So it has to be, this Q1 has to become a minus P1. So this becomes this, and then it is phi P2 has to, I mean, this should have been Q2. So this connect P2 has to become a minus Q2. So this becomes P1 plus P2, and at the outside I'm going to have phi P3 over here and a phi Q3 over here, and this is phi less. So what do I, let's see, the four terms that I have outside, phi less, and P3 is as it was. So P3 is as it was, and a phi less over here, which has become P1 is Q1. So this is what's going on. I have P3, Q1, all right. So this is phi P3, which is less, and this is phi 1, which is minus P1, minus P2, minus P3. The other phi less, just want to make sure that which is minus P3. This is Q3. Q3 has not become anything, right? Neither Q3 nor P3 have become anything because, yeah. So because there is one more step. All right. P1, I have phi P1, phi minus P1, P2, over here. So phi P3 minus P1, minus P2, minus P3. Then there is minus Q3. This is Q3, sorry. This is Q3, and this is phi less, which is minus Q1. And this is plus P2 plus P3, because it is the Q1 which has become minus P1, and then Q2 which has become minus P2. So this is Q3. So I have P1 plus P2 minus Q3. So it is, which is all right. Now all the P's and Q's, they add up to 0 as they must. And now there is the final last bit over here. The last bit is that P1 and minus P1, they have given me a correlator over here, which is like 1 over P1 square plus M square. This has given me 1 over P2 square plus M square over here. Now, what is the momentum that I need at the vertex? I'm interested in a zero momentum vertex, which means that the total momentum over here has got to be 0, and I'm looking at essentially I'm looking at a correction to this over here, where all lines essentially are going to be basically looking at the zero momentum vertex. I'm just looking at the correction to lambda, which I'm going to pick up. The lambda over 4 is going to get corrected by this. The diagram looks like, so this is the diagram that I'm looking at. So it is this part over here, the P1, I mean, if I want the zero momentum vertex, the zero momentum vertex essentially means that all all this is a coupling constant, is a constant which is lambda. It is a constant which is lambda, so which is going to be corrected from here to, I want to pick up the constant, which means that this line, if it has a momentum p, this has a momentum minus p. The total momentum at this vertex is going to be 0. And so you are going to look at what you are interested in is the line which is p square, p over here and minus p over here, giving me a vertex which has a 0 external momentum. You are just looking at this vertex, which is where there is no momentum transfer going on. And therefore, it is just going to be integral, which is integral of 1 over p square plus m square whole square. So your interest is in simply correcting for this, finding the correction to this point strength over here, which is lambda over 4, and the total momentum has got to be equal to 0. So you are looking at this total 0 over momentum vertex over here, and it is these two lines would be carrying 0, which is p square, and these two over here would also have to be carrying 0, and that is the thing which you need. So it is phi p1, phi p minus 1, which is 1 over p square plus m squared. So it is p1 and minus p, p2 and minus p. The contribution that you are getting from just this part over here is, as expected, 1 over p square plus m squared whole square. So the correction to this lambda, the lambda over 4, the next order correction is, there is this 9 lambda over 4. This so 9, you pick up 9 lambda square divided by 4. So there's 1, and then gets this times this integral over here. So what the lambda has gone to is lambda prime, which is lambda minus, and because the first one had a minus sign and this has a plus sign, so when I bring this up, so this has a minus, there is a plus when it goes up, so the lambda by 4 has changed to lambda, and then 4 times what I get from here, which is this 1 over 9 somewhere or other here, this 9 by 4 over here. So it is 9 by 4, it is lambda squared, and I have a dBp. Going from lambda. So that is what happens to the coupling constant. So the mass gets changed, the coupling constant gets changed. So what is happening is that you start out with a theory which was looking like this. After one step of this process of eliminating the wave numbers, what you have is you have eliminated the larger wave numbers so that the scale has become the basic scale unit has become larger, and therefore the measure of the lengths have become smaller. So in terms of the lattice spacing, you are talking about 2 lattice spacings, for example, instead of 4. And in the process, what has happened is that the mass of the original theory has become m prime square, which is this. The coupling constant of the previous theory has become lambda prime, which is this. So,
can we what are 1 by e square m square and square?
Integral alternate, factor. Sorry, sure. It's another factor. Yeah, absolutely. Yeah. Sorry, there was, sorry, thank you. I mean, there was one factor here, P1 and P2 are opposite in sign, and therefore it is. So the zero momentum vertex, no momentum associated with the vertex. So outside lines carry zero momentum, and therefore the inside lines carry. So zero momentum over here, zero momentum over here. The inside total momentum is zero. P1 and P1 equal to minus P2. Very good. So this is the result of this long and but the point is that once you have seen it, I mean, this is what you do for all problems of this kind, and this is the, I mean, this is what you do in every branch of physics. That's the that's why it is useful. We are doing it today for critical phenomena in this fluids or magnets, so that you are looking at large length scales, and you are doing a transformation which essentially leads to this coupling constants, which are, what is happening is that the coupling constants are changing with the length scale. The process that has gone on is that I have changed the length scale, basic scale of the problem, whereas when lambda was the cutoff, it is now all momenta are now scaled down by a factor of b. All physical length scales are scaled up by a factor of b. The scales and the measure has become smaller. The correlation length, if it was, I mean, 10 lattice spacings, is now become 5 lattice spacings, or I mean something smaller. All right. So this is where we are. I mean that, and this has this diagrammatic expansion, which, I mean, you recognize that here is a 2-point function, and therefore, I mean, this is the relevant, I mean, the first order for this partition function. If I draw, you will find that in the first order, there is just this over here. And then in the second order, when I have two coupling constants, as we saw that there were terms which looked like, which I have removed now, there were terms which looked like this and which looked like that. When I expanded that out, these go with this. So what these are the order lambda squared correction to this propagator over here. And the vertex gets corrected the first time, because the vertex is order lambda, the first correction to the vertex comes at order lambda squared. So this is the first step that you take. And but it is the basic point is that your coupling constants flow. I mean, you change the scale and you flow. In this case, you are flowing to a region where the lengths are, the basic length scales are infinitely big. If you were doing high energy physics, you would be flowing to length scales which are infinitesimally small. So the point is that what this becomes, the big connector, all physics, whatever branch you look at, condensed matter physics, high energy physics, intermediate physics of any statistical variety, that statistical fluid mech or whatever you look at, there is just one way of tackling problems, which the one analytics technique which works for all. And that is why I spent a lot of time that if you go through this, I will notice and understand that what basically we are saying, that system has a certain number of minimal parameters that which are the coupling constants of the problem, and these coupling constants change as you change the scale of it, and you can be changing scales to go at large the large length phenomena, or you could changing scales to go to large momentum phenomena. That is the difference. It has its all right. I mean, the philosophy is never changed. That's the point. The technology and the symmetries and so on and so forth, they are what change. Over here, it is a ON symmetry, and that's pretty trivial thing, and therefore the algebraic complications are minimal. But if you are looking at the high energy part, the symmetries would be much more involved, and one would be looking at things which are different. All right, so here we are. But now I have to do, this was the first step. I have written this down and this, but there are two smaller things which I need to do. That if I write like this, the next step, when we did the discrete model, the Ising model, and did the partition, integrate out this pen, integrate out this pen, and so on, it was J going to J prime, which I could write as Fj, and we were through. Over here, I have removed a certain set of degrees of freedom, and by integrating out from lambda over b and this, and I have got generated this over here. But I have to be, I mean, what kind? I'm not over there. It was j. I mean, this is j n plus 1th step equal to fj of n. This is the j at the n plus 1th step. This is the j at the nth step, and you look for the fixed point. That was the structure. Over here, what is it that I'm going to do? Whose fixed point? Which thing? Over here, the convenient thing is to make it flow. What you do is you think of B as very close to unity. So B is very small. So B is very small, and that is the situation that you want to talk about, and therefore what's meant by B being very small? Go back to, let's go back to the Gaussian model. When we did the Gaussian model, the answer was m prime square is equal to m square times a b square. We had integrated out the region from lambda over b less than p less than lambda. This had been integrated out, and the Gaussian model, we found that the exact answer was m prime square is equal to m square plus b square. Suppose this b square B is close to unity. B is equal to, let's say, e to the power delta L, where delta L is very small. Then this m prime squared is equal to m squared e into 1 plus 2 delta L and higher order terms. So in the limit of delta L, so this is m prime squared or minus m squared. So that is delta of m squared is equal to 2m squared delta L. So delta m squared over m by delta L, which is dm squared dl, is equal to 2m squared. M squared is the temperature difference. M squared is T minus Tc by Tc, which is generally denoted like T. So you have the flow equation dt dl is equal to T. So if I did if I considered B very close to unity, then this equation that I had could be written down as one. Now, here is something which I'm doing perturbatively, and I have got this answer. So how do I reconcile? The reconciliation is easiest when B is close to unity. So B is close to unity, and then this term is going to become very small. So B close to unity makes this term over here very small, and what you are going to see is that m prime, all right, and so B over here is close to unity, and m prime squared is equal to m squared plus 3 lambda by 2, and it is lambda over b to lambda ddp by p squared plus m squared. All right. To make B, my focus is that essentially I want to make B much smaller than 1 and make this a flow equation. But let's look at, I have to do something here. That lambda prime is lambda minus 9 lambda squared by 4, and it is integral lambda over b to lambda ddp over p squared plus m squared whole square. So what is what was the if I did this if there was no correction of the 5/4 variety, then your we just noticed that dm squared dl is equal to 2m squared, which, what is the 2? The 2 is, what the 2 is that it is the dimension, of m squared. Where did this 2 come from? One needs to, so you want to understand where this 2 comes from, because it comes totally trivially. Because the dimension of m squared, in terms of length, the dimension of m squared is equal to, I mean, so this whole thing is dimensionless. So it is L to the power, if L is the length, then this is like L to the power minus D dimension of m squared, and then it is dimension of, all right. Question is, what is the dimension of phi? The dimension of L to the power minus D dimension of phi to the power 2, that would have to be L to the power 0. So that is, and then there is L to the power minus 2, which is this, and the dimension of phi square, and then L to the power minus D, which is equal to L to the power 0. That's from that over there. So the phi dimension is equal to L to the power 1 plus D by 2. So dimension of phi is 1 plus D by 2, and therefore the dimension of m squared over here is L to the power D, and then the dimension of phi, so it is L to the power minus 2 minus D equal to L to the power minus 2. So the dimension of m squared is 1 over L square over here, and that immediately tells you that you look at this flow, which is dm square over L, that what this is flowing by is just the dimension. I mean, it immediately tells you that if the dimension of this is L, then if I change things by a factor of b, things will change by b squared. If b is close to there, therefore it is going to be this. Now, what happens for lambda? We know what lambda is. Lambda has the dimension which is L to the power minus 4 minus D. So that which is, so lambda, therefore the d lambda dl, if I don't do anything else, just by the scale change over here, the d lambda dl is going to be equal to 4 minus D times lambda. Right? So 4 minus that is over here. I have not done the scale change yet. All that I have done over here is that I have simply integrated out the some degrees of freedom. After integrating out the degrees of freedom, the next step would be that do a scale transformation. The scale, that is the m prime, I mean, would have to they would have to change according to their this scale transformation. Doing the scale transformation what it would do is that it would change dm squared dl as 2m squared. This is just the scale transformation. And this is just the scale transformation. After the scale transformation, this is m prime square which happens for lambda equal to 0. I mean, the scale transformation does not require the lambda. This is just the naive scaling of the free energy that you started out with. So there is dm squared dl equal to 2m squared, and then the additional part is this flow over here, which is the the additional part of the flow is what you see over here, this 3 lambda over 2 dl. The d lambda dl, on the other hand, the lambda prime has changed in this fashion over here, and d lambda dl, that's the additional part. This is just the diagram moving out degrees of freedom. So that is given me this. But now the naive dimension by which one would have to scale things to restore the cutoff so that to lambda, so that I can go ahead and do the thing once again. That factor for this is 4 minus D. So d lambda dl 4 minus d lambda exists in addition to the d lambda that you are looking at over here. There is a delta lambda over here which has come from the diagrammatics. There is a delta m square which has come from the diagrammatics. That is the part of what has come from removing certain degrees of freedom. But then there is a question of restoring the problem back to the old cutoffs, which is governed by the actual dimension, naive dimension of these quantities m square and l square. So that is the step 2. There were 3 degrees, 3 steps that one had to do. Remove degrees of freedom. So that was one, and then was restore the old cutoff. So you restore the old cutoff, you have to bring things up by by the naive dimension, and so it is what comes out over here. So this is dm squared, this flows as dm squared, this flows like this, and now in addition you pick up this over here and you pick up this over here. So when you write the whole thing, then the point is that the flow is going to be given by dm squared dl is 2m squared. This is just from the naive dimension of the operator, plus 3 lambda by 2 integral lambda over b2 lambda ddp over and no, integral is because that is the derivative. I mean, it is d lambda, delta lambda. And over here, it is d lambda dl is equal to 4 minus d lambda, and then I have picked up additional form part, which is lambda over here, z lambda to b to lambda ddp over t squared. So that is the renormalization group flow for m square and lambda to this. So now what? Now you're still, I mean, they're faced with this. Nothing you can do. What is d? I mean, where in what d? I mean, am I going to calculate in d equal to 3, or what am I going to do? And what is lambda? So, well, what is lambda? Now comes the question that this flow, what does, now you come back to what was your question when we did the now go back to the question of when we did the Ising model and got jn plus 1th step as f of jn. The thing which we looked for was j star, the fixed point. So you have to look for the fixed point over here. Yeah. So the fixed point corresponds to dm squared dl over lambda this equal. Right? So that would be the fixed point that you would be looking at. So, all right. So now I have to, as soon as I start talking about that, I have to actually make clear this part of it. This B is still sitting over here, but which I have to obviously. I mean, it's a minus m prime square was m square plus this, just as lambda prime over here. And I have to worry about when I wrote m prime minus m square and just glibly wrote it down as dm squared dl. There was a delta L business that I was also doing over here, which I did not. But we'll come to that in a minute. Yeah, well, but here the everything. I mean, how do I control what is lambda? Why is lambda small? That is, when is lambda small? Nothing would happen unless lambda is small. Now you note that fixed point, I have to work near a fixed point. Fixed point is dm squared dl equal to 0, d lambda dl equal to 0. So d lambda, as soon as I go to dl, d lambda equal to 0, I notice that I can get a fixed point because if 4 minus d is small. So fixed point FPT, which makes lambda small, is the one near d equal to 4. So lambda expansion is in orders of lambda. My expansion is controlled only if lambda is controlled. And where do I want the expansion to work? It is near the fixed point. So so what do I do? I look for where the fixed point is. The fixed point happens to be of order lambda, of order 4 minus d. Which is the fixed point for the coupling constant is of order 4 minus d. The coupling constant, therefore, will become small if d is close to 4. And since the perturbation theory has to be arranged in powers of 4 minus d, which is generally the 4 minus d is epsilon. And what you would find is what one calls the epsilon expansion. So epsilon expansion, because I need this at the fixed point, and that is near the fixed point. Fixed point is criticality. So fixed point is when the system has gone to the critical point. Either xi has become the correlation length has become infinite, or the correlation length has become 0. If the correlation length is 0, it's an unstable fixed point, and that is the one we would be looking at. But fixed point we will look at, and fixed point is ordered, the lambda would have to be at near its fixed point value. Fixed point value is of order epsilon, and thereby comes the control parameter of this expansion. You control the expansion by epsilon. Obviously, the answer is required at epsilon equal to 1. So things are going to be tricky. If you are lucky, it will work. If you are unlucky, it won't work, and things like that. Certainly, I mean, 1 or 2 orders is what you can bank on, because if the order of epsilon is big and you go to large orders, I mean, nothing is going to happen. You are not going to be very successful. So, I mean, all right, a lot of it is luck. If it works, great. If it does not work, too bad. I mean, you have to, but this is the philosophy. So there is a little bit left. that I have to, we have set up the ground rules. It is a few more minutes. So before I start talking about real gases with which do scatter off each other, I'll finish up this as a couple of integrals to be done and the exponent. Nothing much left, but this, go over it, and we are really near the end, and so whatever you can think of as whatever is not clear and not, one more discussion would help. Please, before you come, on Friday, have a look at what we have gone through. We are really on the verge of that. Okay. So, unless or the point is it now declare, I can't evaluate. I have to evaluate this. I have to know D. So now I can evaluate at D equal to 4. Before this I can't.
সেগুলো লোয়ার ডিপ জন্য কাজ করে, কিন্তু মানে ফর হায়ার ডি তো ওগুলো কাজ করে, মানে আপনাকে স্টার্ট আউট করতে হবে।
হায়ার ডি মানে
for d let's say 6 7 8,
no, এখানে তো বলে দিচ্ছে you don't have lambda equal to 0.
So 6 7 8 এর জন্য I guess extra terms আসবে, মানে
no, equal to 6 7 8 is simply this Gaussian. Lambda goes to lambda fixed point goes to 0.
Sir, D let's say for very small, let's say 1 2
below 2 is the only place where Ising should be working, but does very badly. And the continuous structure, it is not supposed to work at D equal to 2, because there is no phase transition except for the right side. So D equal to 2, n equal to 1, which is we are essentially doing n equal to 1 solving like systems. So D equal to 2 there, but it gives rubbish in D equal to 2, and epsilon has to come. So perturbation theory gives rubbish. So it's only D equal to 1. D equal to 4 and Messian at lambda flows to 0. No coupling. So lambda 1, so it's constant.
Without partition, কিছুই করা
without either computation or if you are very good and very lucky, then it is exact solution.
মানে স্ট্রং মানে কাপলিং জিনিসপত্রতে তোমার এর কাপলিং কনসেপ্টটা মানে বড়, সেই ক্ষেত্রে গুলোতে খাটবে
না, সেক্ষেত্রে তো খাটবে না, কিন্তু অনেক সময় যে যে স্ট্রং কাপলিং কনস্ট্যান্টটাকে 1 over lambda করে যে প্রবলেমটা মানে সেখানে we can get some information. consider that, right, it's the efficiency of 4